Okay, let's jump right into this explainer. Today, we're looking at a completely groundbreaking waste-to-wealth technology. I mean, we're talking about a process that could absolutely reshape environmental policy and how industries manage resources. We're going to see how taking two of the globe's most stubborn, problematic waste streams and literally forcing them to work together can actually produce high-value energy precursors. It's really fascinating stuff. So here's our roadmap for today. We've got 1, the global waste crisis; 2, co-pyrolysis, a synergy solution; 3, analyzing the chemical conversion; 4, the optimal recovery recipe; and finally, 5, scaling for industrial wealth. Let's get right to it. All right, Section 1, the global waste crisis. We're looking at the massive scale of plastic and biomass waste. Now, before we talk solutions, we really need to wrap our heads around the sheer scale of this waste. I mean, we're all pretty familiar with everyday plastics piling up in landfills and incinerators, right? But there's another hidden giant we need to talk about: lignin. Worldwide, we are producing a staggering 150 billion tons of it. 150 billion! So what exactly is it? Well, lignin is the super complex, highly stable component of plant biomass. It's basically a massive byproduct of industrial wood processing, like paper making. And here's the crazy part. Almost 95% of this lignin waste is just dumped straight into rivers or burned. It's a huge environmental burden and, frankly, a complete waste of potential energy. And you can see the dual problem we're facing right here. On one hand, we've got everyday plastic polymers, packaging, canisters, agricultural films, just suffocating our landfills. And on the other hand, we have this highly stable, non-degradable industrial lignin powder. Both are for sure incredible environmental liabilities. But as folks thinking about environmental policy and innovation, we really have to ask, what if these two massive liabilities could somehow cancel each other out? Which brings us to Section 2, Co-Pyrolysis, a synergy solution. How two waste streams literally break each other down. What's really exciting here is how we can take one massive waste problem and use it to solve another. We do this through a process called co-pyrolysis. Now, what is that? Basically, it's a thermochemical conversion technology. In plain English, we heat multiple waste materials together in an environment with absolutely no oxygen. It's simple, it's eco-friendly, and it's cost-efficient because blending these materials actually accelerates the thermal reactions. But you might be wondering, why blend them at all? Why not just process the plastic and the lignin separately? Well, this comparison hits the nail on the head. Think of lignin as a super stubborn vault of energy. If you try to heat lignin all by itself, its complex chemical bonds just resist breaking down. It repolymerizes and leaves behind this massive, totally inefficient solid char residue, over 50% char actually. But plastic acts like the key. See, plastics are packed with hydrogen. When they heat up and break down, they release hydrogen radicals. So when you add these plastic radicals into the mix, they essentially unlock that stubborn lignin vault. They stabilize the lignin fragments so they don't turn into char. Instead, both the plastic and the lignin are transformed into really valuable, lightweight hydrocarbons. It's pure synergy. Moving on to Section 3, analyzing the chemical conversion, proving the efficiency of this valorization process. Now, to show you that this isn't just some theoretical scientific novelty, researchers backed it up using a really rigorous 3-step analytical method. First, they used thermogravimetric analysis, or TGA, which tracks mass loss as temperatures rise. Next, they used TGFTIR to monitor the functional groups of the gases evolving in real time. And finally, PyGC/MS, which pinpoints the exact final chemical composition. Basically, they're tracking exactly what is happening at every single millisecond of the reaction. And the key takeaway is right here. These TGA curves literally map out the mass loss. Remember how I mentioned that lignin alone leaves over 50% char? Well, look what happens when lignin is mixed with high-density polyethylene, or HDPE plastic. That residual mass drops to just 10%. 10%! The plastic successfully triggered the disintegration of the lignin's chemical structure, proving beyond a doubt that this synergy dramatically reduces solid waste. On top of that, the TGFTIR analysis actually evaluates the gases as they're released, and it proves that instead of just emitting a bunch of useless gases, these specific mixtures successfully create targeted aromatic and aliphatic hydrocarbons. So the science absolutely confirms it. The reaction works exactly as intended, massively enhancing the chemical conversion efficiency. All right, Section 4, the optimal recovery recipe. Finding the sweet spot for maximum hydrocarbon yield. Now, if you're crafting environmental or industrial policies, you can't just toss random amounts of waste into a furnace and cross your fingers, right? You need an exact formula. And this chart shows us the ultimate sweet spot. The researchers tested different mass ratios of lignin to plastic. At a 1-to-1 ratio, the yield is pretty low. There just isn't quite enough hydrogen from the plastic to stabilize the lignin. A 1-to-2 ratio gets a bit better. But when you shift that mass ratio to 1 part lignin and 3 parts plastic, that is the absolute perfect balance. That 1-to-3 ratio provides exactly the right amount of hydrogen radicals to maximize hydrocarbon recovery, pushing yields all the way up to nearly 40%. And the magic temperature for this 1-to-3 ratio? Exactly 600 degrees Celsius. Why 600? Well, it perfectly drives the cracking of both the polymer chains and the lignin's aromatic structures. If you go lower, say 550 degrees, the lignin doesn't fully break down. But if you push it too hot, up to 650 degrees, you get what's called overcracking, where your really valuable large hydrocarbons just break apart into smaller, much less useful gases. So, 600 degrees Celsius is our confirmed optimal thermal sweet spot. Which leads us into Section 5, scaling for industrial wealth, generating valuable precursors for tomorrow's bioeconomy. So, why does this specific chemical output actually matter for future policy investment? Well, by optimizing this co-pyrolysis at a 1-to-3 ratio and 600 degrees, we aren't just making waste disappear. We are literally generating high-value industrial precursors. The data shows we're recovering heavy hydrocarbons like octadecane. N-octadecane is highly sought after as a precursor for advanced biofuel production. Plus, because of their high melting points, they're fantastic phase change materials used for thermal energy storage. We're even capturing valuable aromatic compounds that have direct real-world applications in the pharmaceutical and chemical industries. It's a real game changer. So as we wrap up this explainer, the data leaves us with this unavoidable truth. We have millions of tons of plastic and billions of tons of lignin literally choking our environment. Yet when we bring them together, they hold the exact keys to unlocking high-value bio-based energy resources. So, for those of you shaping our future, the question is clear. How will your environmental policies adapt to turn tomorrow's massive waste pollution into tomorrow's industrial power? Thanks so much for joining me for this explainer. Keep asking those great questions, and I'll catch you in the next one.